All right, so welcome to the 11th lecture in this course on algebraic topology. I'm WIldberger at the University of New South Wales. Today we're going to talk about rational curvature and winding numbers and turning numbers of curves in the plane. So I'm going to give a non-standard view of curvature. So the formulas that I'm going to introduce today are not found in textbooks on the subject. And I propose that the formulas that you're going to learn are going to be new and better. So it comes down, I suppose, to the notion of an angle in the plane, which is quite a problematic historical notion, actually. And in current usage, angles are used for two things. They're used in geometry and in trigonometry. And they're also used in discussing circular motion or certain types of problems involving what one might call angle chasing. And curvature also falls into this aspect of things. Now, these two aspects of the angle usage are often mixed in modern formulation, but I think it's better to separate them very clearly. And instead of angle for geometry and trigonometry, as you may know, I much prefer the notion of spread found in rational trigonometry, which allows you to solve almost all those problems much simpler and a better way. Over here, when we're talking about circular motion or rotations or angle chasing, I'm also now going to introduce a new variant on an angle, which is a rescaling. So it's better to rescale. So to introduce this idea, and this will be a little bit novel for you, okay, so you may have to just take a big breath and prepare yourself to think a little bit differently about something that you've been trained to think about in a certain way for many years. Okay. So we're going to start with this question here. Suppose that we have a vector that's rotated from this position to the perpendicular position here. Okay, so this is the start, this is the end, and the question we want to ask is how to describe the amount of turning represented by this motion. Okay, you're all familiar with an answer. So the standard answer is that we measure it with an angle, and that angle is pi by 2. And that has some decimal expansion, which I don't know. So it's 3.1415 blah, 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 divided by 2. So that's some other decimal expansion. I suppose it starts at 1.5 dot, dot, dot. Now this decimal expansion is a real number. It's a very complicated real number. In fact, it goes on trillions and trillions of places. If you actually had to read through this, you might get a sense of the complexity inherent in that. We're cheating in a little way by simply thinking about that symbol and not thinking about this infinite decimal, which is actually very, very complicated. That's actually not historically the standard answer. Historically, there's a much older answer. Let's call it answer number 2. Answer number 2 is that the angle is 90 degrees. That, of course, goes back to the Babylonians. And it has much to recommend it. In particular, it makes talking about 30 degrees or 60 degrees or 45 degrees relatively pleasant. But it's still a little bit arbitrary. Why choose 90 instead of 1,000 or something else? There's another system where one talks about 100. I think it's a system found in Europe in some places where one has a sort of a metrical approach to this. But in my point of view, none of these is the right answer. There is a fourth answer, which is much more natural and just better. All right? So if you're watching this video at home, I want you to pause it now and go off into a quiet room and think for yourself for 10 or minutes or half an hour, and think if you had to start right from the beginning and you had to say, how much turning is that? What is the right answer to that question? It's a number. Class, any guesses to what that number might be?
1.
That's not a bad guess. Quarter. Half. Oh, let's do this democratically. How many for a quarter? How many for a half? 1. Others? Looks like a quarter is going to win. And I propose that that is, in fact, the right answer. That's how you should have learned angles back in public school. Okay, so this has a lot of implications. Now we need to rescale and rethink what we've learned about angles and various formulas having to do with polygons and so on. And then we're going to get to curvature and turning numbers and winding numbers, and we're going to use this rescaled system. So let's think about what we're really doing. Well, we're regarding this natural turn all the way around as the basic unit. So this is a turn of 1. That's the basic unit. And if we have a more general, say, angle, let's say we'll draw a circle, and let's say we have going from there to there. And let's denote now this turning, this rescaled angle, by an arc with a little arrow in the middle rather than at the end. And let's denote it by tau for turning. Then in this case, the tau can be defined as a ratio of 2 displacements. The displacement, this one, divided by the unit displacement. So tau is a ratio of rotational displacements this one divided by the big one, or big one being 1. So it's not something that you get by taking a length and dividing by a radius. That's the usual definition of an angle. It's, at least in the radian system, it's the length of this circular piece divided by the radius of the circle. This is not a very good definition for a number of reasons. First of all, it depends on a profound geometrical result, namely that this ratio is independent of the size of the circle. So you need a prior theory of Euclidean geometry to be able to establish that theorem. Secondly, when we go to talking about rotations on a sphere, let's say, if we're at a point, say, there, and we're interested in what is the turn between this line and this line, say, going from here to here, if we try the same trick by drawing a circle and then looking at a ratio of circumference over length, we find that, in fact, the proportion is not independent of the circle. There's not a linear relationship between these things. The correct relationship is the relationship between this amount of turning and the whole turning. And that notion works on a sphere just as well as it does on a plane, just as well as it does on a hyperbola. All right, so let's do some basic things now with this idea of turning. Let's give it a name, perhaps. So we'll call this tau the turn angle, because it's still an angle. It's just normalized. Or maybe T angle, or maybe if we're really short, we can just write tangle. Okay. So this would be a tangle of roughly how much? Maybe a third. Okay. It's 1/3 of the way around, so we would say this is a tangle of 1/3 in this particular case. All right, so let's practice this a little bit. So, well, we've already said that's a tangle of 1/4. This is going to be a tangle of 1/2. If we have an equilateral triangle, then each of these turn angles, well, I'm supposed to do it like this. Each of these is the same. They're all going in the positive direction. How much would that be? 1/6. What about if we go in the opposite direction? So we go from here to here. Well, let's agree that that's a turn in the negative direction. We want to distinguish that from this one here. So we'll say that's a turn angle of -1/4. What if we go all the way around and then back up to the perpendicular position? Well, that's a turn of 1, and that's a turn of 1/4, so that's altogether a turn of 5/4. If we have some turn of tau there, then what is this complementary turn? Well, they're both going in the same direction, and they have to add up to 1/2. So that should be 1/2 minus tau. All right, so we've got enough now to talk about the basic formula that you've all learned in school, the sum of the angles of a triangle. So now we're more interested in the sum of the turn angles of the triangle. And we'll orient them to be all positive. So this is the positive direction, and that's the negative direction by convention. And so we'll just talk about positive ones. So let's call that one, say, tau 1, and that one, sorry, tau 2, and that one, tau 3. Then how do we figure out what the sum of these turn angles is? Well, a good way of thinking about that is to think in terms of the complementary tangles. So if we extend that one, and then we extend that one, we extend that one. And we imagine having a vector that's, say, initially pointing in this direction. Okay. And we're going to rotate this vector. So it's like this. And then we're going to move it over here. And then we're going to rotate it till it's like this. And then we're going to move it up here and rotate it till it's like this. And that's back to where we started. So if we call this external turn angle, say mu1, and this one mu2, and this one mu3, then what we've just said is that mu1 plus mu2 plus mu3 is all the way around. That's a turn of 1. But also the relationships here are that tau 1 plus mu 1 equals a half, because that sums up to what we usually call 180 degrees, or a straight line. Tau 2 plus mu 2 equals a half, and tau 3 plus mu 3 equals a half. Then if we add these various formulas, tau 1 plus tau 2 plus tau 3 equals, well, we have 3 halves on this side. The sum of the mu's is 1. And so we're going to get 1/2 for the sum of the turn angles. Let's do a quadrilateral. Same kind of story. So we'll suppose we have one turn angle tau 1, tau 2, tau 3, and tau 4. We have the external tangles mu 1, mu 2, mu 3, and mu 4. So then the situation here now is that the sum of the external turn angles, mu 1 up to mu 4, is again 1, because we're starting here, and then we're going 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 here. So we've got the external vector has gone all the way around once. So that's the critical thing that we can measure. It's the sum of the external turn angles. That's equal to 1. And otherwise, the relations are just as before. Tau 1 plus mu 1 equals a half. Tau 2 plus mu 2 equals a half. Tau 3 plus mu 3 equals a half. Tau 4 plus mu 4 equals a half. And when we add them all up, tau 1 plus tau 2 plus tau 3 plus tau 4 is going to be equal to, well, now there are 4 halves, which is a total of 2. And we have to subtract the sum of the mu's, which is 1. So we get 1 for the sum of the interior turn angles of a quadrilateral. And now I think it's pretty clear that we can generalize this to a general polygon. So suppose we have an n-gon. With tau 1, tau 2, etc., up to tau n. External turn angles mu 1, mu 2, up to mu n. So exactly the same thing will happen. Mu 1 plus mu 2 all the way up to mu n will be equal to 1, since we're going all the way around with our vector. And at every vertex we have exactly the same relation. T1 plus mu 1 equals a half, down to Tn plus mu n equals a half. And so when we add those all up, we get T1 plus tau 1 plus tau 2 plus tau n equals, now there are n of these, so n over 2 minus 1, the sum of the taus. So that's now formula for the sum of the internal turn, or the total amount of turn inside a polygon. Well, a convex polygon. But we can also think about generalizing this, because we don't mind turns which are more than 1 or less than 0. We're just working algebraically. So let's do something a little bit different. Let's consider a very famous non-convex polygon, where we're still thinking of having only 5 vertices and 5 edges. So these intersections are not real intersections. Okay. So, well, we can still think about applying the same reasoning. let's say we start here. So that would be tau 1, and that would be mu 1. And then there'd be a tau 2. I suppose that would be mu 2. And so on. There'll be a tau 3, and a tau 4, and a tau 5. And now the same argument is going to apply, but there's going to be a slight difference. The difference is what happens when we look at our external vector. So we're starting, let's say, in this position here with our external vector. Now as we go around, watch what happens. So we're making this turn first, and then we're going here, and then we're going here. Now we've crossed, we've already done a little bit more than one turn. We started here, and now we're over here. And then we keep going, and then over here. And we're back to where we started. And if you're just watching the pen, it's gone around twice. It's gone around twice now. So that the sum of the external tangles is 2. Otherwise, the relationships are exactly the same as before. So tau 1 plus mu 1 equals a half, down to tau 5 plus mu 5 equals a half. And so now in this case, tau 1 all the way up to tau 5 is going to be the sum of the halves. So there's still 5 of them, 5 halves, minus the sum of the mu's, which is now 2. Which is a total of a half. And by the way, since each of these is supposed to be symmetrical, suppose this is a regular pentagram, then it implies that each of the taus is equal to 1/10, because there are 5 of them adding up to a half. So there's a more general relation here that we see, that if we have a more general polygon, which is not necessarily convex, so a general n-gon, which is perhaps doing something like this, we can still talk about tau 1, tau 2, and so on. So we can still talk about tau 1 all the way up to tau n. And the same argument is going to show that we're going to have n minus 2 minus, well, the total number of times that our external vector has gone around. So we might say tau of p. P is the polygon, where tau of p is the number of times the external vector has turned around. Now one could convert all this discussion to the usual angles by just remembering that the relationship between our turn angle and the standard angle is, well, we take the standard angle and we divide by 2 pi. So it's easy to convert any of these expressions to a more familiar angle, a more familiar formula involving pi's, but why would you want to? It's more natural this way. And we'll see that it's actually more useful in this way too when we go to polytopes and where things become a little bit more complicated. Okay, so before I leave polygons, there's an important alternate way of thinking about this, the relationship between the internal turn angles and the external ones. Let's just do it with a triangle. So here's a triangle, and I have turn angle tau 1 there, and tau 2, and a tau 3 there. Now the alternate way is to think about not what a tangent vector is doing, which is sort of what we've been doing up till now. We've been following the path of the polygon with our tangent vector, but all to think instead of a normal vector. So let's say at this point there is a normal vector, and there's another normal vector. And if we follow the normal vector around, well, the normal vector just stays where it is. That's parallel. And then over here it swings around to this one. And over here we have a normal vector and another normal vector. And so we have actually 3 external normal turnings, which are, let's call it mu1 and mu2 and mu3. I'm using the same notation as before because they have the same values as the other mu's that I were considering. Why is that? Well, because this turn here of 90 degrees or a quarter is really a quarter turn, and that's a quarter turn. All the way around is 1, and so this turn tau 1 and this turn mu1 must still add up to a half. So we could have reframed this prior discussion in terms of how much the normal turning is going on. And that has a nice interpretation as a curvature quantity. So we define, say, mu1 to be the curvature of the triangle at the vertex A1, let's say. Suppose that's A1 there. Well, it's not curvature in the usual sense. It's a kind of a rescaled curvature, so I should maybe put rational curvature here. Okay? This is a slightly different form of curvature than you usually find in text on the subject. But it's only a rescaling by 2 pi. And so what we could interpret this, what's going on here, as really a statement in terms of curvature. We can say that the total curvature of a triangle, or in fact a general convex polygon, is namely the sum of these external curvatures. That's equal to 1. So let's have a look at this kind of notion of curvature. So how much curvature does this polygon have? It's a square. It's supposed to be a square. It's something like this. But at this point here, what's the curvature? Right, so here's our formula here. It's the amount of turning formed by the perpendiculars. Perpendiculars would be these ones here, and that amount of turning is a quarter. So the curvature here is a quarter. What about the amount of curvature here? So this is our polygon with a kind of a straight edge. How much curvature is there here at this vertex? 0, right? The curvature here is 0. Because the 2 perpendiculars are parallel. There's no turning between the perpendiculars, which is as it should be. That should be curvature 0. So all of the formulas that I derived for the circle, quadrilateral, pentagon, and so on are really contained in this formula for the total curvature. It's maybe more interesting than the sum of the interior angles or interior turn angles. What's the total curvature? But that's only for a convex polygon. Of course, if the polygon does something different, then we have a different amount of total curvature. All right, so now armed with this, let's talk about winding numbers. Winding numbers of a curve. So what we're doing now is we're considering a curve in the plane, and it doesn't have to be convex, and we give it some direction. So that's its direction. Let's call the curve gamma. And we choose a point. We're going to choose a point, and let's call that point there the point that we're talking about the winding number with respect to. So we're going to define the winding number of the curve with respect to the point O to be the total amount of turning of the vector OP, where P is on the curve. So what we're going to do is we're going to, here's our reference point. We're going to look at the vector joining O to P, and we're going to watch that vector and see what happens as we go around the curve. Okay? So I'm just going to follow the curve, and you can see what happens to our vector. You agree that it's gone around once at that stage? So from here to here, it's gone around once. Okay, now as I keep going, okay, now it does a little diddle, but it goes back there. It's altogether gone around twice. So this vector here, it's gone all the way around, maybe not uniformly, it's gone backwards and forwards a little bit, but it's gone all the way around twice. Well, I could represent that by a loop like that. There's the center, there's our vector, it's gone around twice. So there's our representation of the turning, and the total turn here is equal to 2. And this can be represented or thought of as the sum of turns of individual pieces. Individual segments of the curve. So if we broke up the curve into pieces, we could talk about the amount of turning of any piece. So say for this piece from here to here, we're talking about the turning from here to here. That would be a certain amount of turning, exactly in the sense of turn angle that we've been talking about. And then the total turning is simply the sum of all those turns of individual pieces. Now this notion of amount of turning depends very much on the point that we're talking about. So let me draw that curve roughly again. And we're going this way. So here, at this point here, we said the turning was 2. And that's going to be the same for any point near that origin. Oh, if we move that origin a little bit, it's not going to change. However, if we change to a point over here, the turning will change. What's the turning, say, with respect to this point? Okay, so I'm going to just follow it. How far have I gone around? Once. So the turning here is once. What about at this point here? Okay, let's follow it. So what's the vector done? Yes, it's gone. Right, it sort of went like this, and then it went around like this once, and then it did a little fiddle. But basically, it went around once like this. That's in the negative direction. So that's a turn of -1 at this point. What else is there? How about this point here? So we're going this way. Okay, so follow along here. Two. And I guess finally, what about over here? See, right, if we follow this around, it's going to be swinging back and forth, but it's never going all the way around. So the turn here is 0. Okay, there must be a little bit more efficient way of computing these various turning numbers, and there is. So what we can do is think a little bit about our vector. So let's do a little bit more complicated example. Okay, so give the orientation here. Okay, there's a more complicated curve. And I want to know, let us say, what's the turning number at this point right here? Okay, so the idea to make it simpler to find out this quantity is to imagine someone having a look at this vector. Let's say we start up here, and this vector is going around. We want to count how many times this vector is going around. So if you imagine over here, we have a copy of where the vector is moving. So we can just concentrate on the vector. So we have our friend over here. We're starting, let's say, in this position. So let's say we start right there, start there. So at this point, our vector is exactly in the north position. And we station our friend there. As we move around, this vector moves around. And the friend does not pay any attention to what this vector is doing except in the neighborhood of this north pole. The friend is only going to count how many times this vector swings past the north pole. And if it swings around this way, he's going to count plus. And if it swings around this way, he's going to count minus. So if the vector is doing something like this, he ignores all of this. Oh, there's a plus because we just went in this direction. And then a little bit later it goes like that. Well, that's a minus, or there's a total of 0 up till now. And then a little bit later there's a one like this. Well, that's a plus. And then a little later there's another one like this. That's another plus. Right? So it suffices to not pay any attention to this vector except near the North Pole. We can forget about the rest of it. And just observe whether we're crossing the North Pole in this direction or in this direction. All right, so let's do that in this example. Okay, so we're starting here. So what about right there? So the vector is going in this direction here. You agree that that's in the plus direction? Okay, so when's the next time that we're going to get to the vector's going to be pointing north? Well, there's going to be a position right there, right? And there's going to be a position right there and a position right there, and that's it. Those are the only places where the vector is in the north direction. So all we need to do is see which way it's crossing that north in each of those examples. So here it was plus. What about this one here? That's also plus because it's crossing in this direction. The direction of the curve is along here. What about over here in this branch? That's also a plus. And this branch here, let's see that we were going in this direction here, that's a minus. So our friend who's recording this thing over here will record 3 pluses, namely when we go through these 3 positions, and 1 minus when we go through that position, for a total of 2. So with respect to that point there, the curvature of our curve gamma with respect to O will be plus, 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 minus, so in other words, 2. So that's the winding number of a curve. Okay, so there's now a related notion, but slightly different, called a turning number of a curve. Turning number of a smooth curve. It's important that we realize this is a more restricted notion, the turning number. Now we're talking about a smooth curve. That means one where smooth curve at each point we have a non-zero tangent vector. Well, those examples that I did also worked, but this winding number business also works for a polygon, for example. The turning number, we're going to require that our curve have a tangent vector, and we might as well give it a standard size, say a unit tangent vector. So we're thinking at each point there's a vector of the same direction, that's the same length, that's following the curve and pointing in the direction that it's going. Okay, so now the idea is what we're going to do is we're just going to concentrate on the tangent vectors. And we're going to, over here, have a look at, on the unit circle, what's happening to the tangent vectors as we go around. So for example here, that's the tangent vector at the point A. Well, when we get to the point B, then the tangent vector will have moved some position like this. Right, so basically we're doing the same thing like we're doing with the winding number, but instead of thinking about a vector from a fixed point to a point on the curve, we're thinking about the motion of the tangent vector itself. Okay, so let's see what happens to the tangent vector for this curve. So here we go. Okay, if I'm here, let me just see if I can try to more or less indicate what the tangent vector is doing. It's already down here. Here it'll be up. Okay, and then it'll be like this, up, and then over here, down there. Okay, you know, etc. Right? In other words, basically, I'm following what this vector does. And translating that vector over here at all times and just watching what it's doing. And the turning number of this curve is the number of times that thing turns around, or the total turn angle that it makes. So tau of the curve is the total turn of the unit tangent vector. is there a snappy way of figuring out what this is in the same way that we did with the winding numbers? Well, there is. We just concentrate again on one particular position of the tangent vector. Let's say, for the sake of argument, north. Okay, so we'll only concentrate on when is the tangent vector in the north position. So where are those points? Well, there will be one point, such point right there. There's a tangent vector pointing north. And where's the next position? Right here. I should do this in a slightly different color. Okay, so there's one north-facing tangent vector. There's another north. Not quite. I guess one over here. That's it, only those three. Now, okay, but those three positions of north correspond to when the tangent vector goes through this point. But the question is, does it go through in this direction, or does it go through in this direction? And what would that mean? Well, this direction would count positive, and this direction would count negative. How are we going to tell a positive turning when it's going like this? When it's going like this. That means it's starting in a position like this and ending in a position like this. So that sort of corresponds to a situation where the curve is doing something like this. That's a plus. It records a plus for us. While going in this direction is a case where the tangent vector is moving through the north in this direction. That would correspond to, I guess, all of our plus. But if it had been something like, if at some point the curve had gone like this, then there would also have been a north, and then the previous one would have been in this side, and the one after would have been on this side, so we would have been going in this direction. So this would have counted for a minus, and that counts for a plus. So to get the total turning number of this curve, we are going to count pluses and minus. What's this one? I think they're all pluses in this case. Plus, plus, plus. And so the turning number of this example was 3. All right, so these are very basic aspects of curves. They almost belong to calculus in a way, amount of turning. Next time we're going to apply, there's a very rich family of applications of winding numbers, turning numbers, including the most important application of all of algebraic topology. Right? So of all the various applications of algebraic topology, there's one that's most important, and we're going to be able to do it just from winding numbers of curves. So we'll do that next time. See you then.